change this. So we did look at that, right? So at the end of the day, you have to make a copy, and there's just an energy to pay for that. So the work to make that copy doesn't change. Of course, what will change if you make it more or less sensitive is that you increase the steepness of your response. And that will propagate towards how accurately you can sense, right? So in that aspect, from that perspective, it's certainly true that how much your system is in the zero-order regime will affect the precision of sensing. Yeah. So we didn't
let me
go down that road. Yeah.
Just keep the rest of the question, Jake, until the coffee break. I'm sure that there will be a lot of intriguing discussions then. Andrew Duncan from Imperial College will talk to us about hybrid modeling of stochastic chemical kinetics.
Thanks. Let me just set this up. So many thanks for the wait. Okay. So many thanks for the opportunity to speak. So this is joint work with Radek and Kostas, who are both organizers of this workshop. And so today I'll basically talk about two hybrid algorithms for simulating stochastic chemical kinetics of the non-spatial variety, as stipulated by the workshop. And yeah, so I apologize. I realize some of you this might be the third time you have seen this talk, because Kostas gave it twice for this Newton Institute thing, so he kind of preempted me. But nonetheless, this will be a bit different, and also it's still very new work, so I would really appreciate people's feedback. Okay, so let's talk about some motivation. Okay, so the motivation is very familiar to I think everyone in the audience. For all intents and purposes, chemical events are effectively random events, such as binding and dissociation, and these will lead to fluctuations in chemical concentrations, and these are what we effectively call intrinsic noise. Now, if you have systems with large volume and large concentrations, these are not necessarily significant effects, but in the cell, for example, or other small volume chemical systems, this molecular discreteness plays a big role, and this is what effectively motivates the study of stochastic kinetics. So a very well-known example here is this little. Sorry, maybe I can just. Is there a pointer in here? Okay. Oh wait, there's one here. Just need the laser pointer. No. If there's one in here, I'll use it. Oh yeah, thanks.
You have to switch it on.
You got to switch it on?
Yeah, I got it. Lovely, thank you very much. So this is a quite well-known example of a circadian clock built on made out of two chemical species, a protein activator and a repressor. And so if you were to look at the deterministic version, the reaction rate equations, what you will see is that basically, starting from a point, you will get this single excursion, and then it will settle in a stable at a stable node. But if you have molecular fluctuations, what will happen is that it will be able to escape from that stable state, and you get these nice periodic cycles. And indeed, there are many other phenomena which can be very adequately explained by noise phenomena, such as metastability, of course. This is noise-induced oscillation here, noise-induced synchronization, and so various other examples. And okay, so like I think most of the talks in this workshop, we're going to be in the well-stirred kind of model. So we assume that we have a reactor with constant volume, which is fixed, systems in thermal equilibriums, well stirred, and we know that this can be so. Under these assumptions, the dynamics of the copy numbers can actually be described by a continuous time Markov jump process. So in particular, given if we have a system of n chemical species which are interacting by, say, R reactions of this form, then we know that the waiting time between reactions are going to be exponentially distributed with a rate lambda k xt, where these lambda k's are the propensities of the reactions, and those, so we know that those will satisfy mass action kinetics. And so associated with each reaction, there'll be a so-called stoichiometric vector, which will give the net change in copy number after that reaction occurs. Okay. So this model can be very elegantly expressed in terms of a sum of R independent time change unit Poisson process. So if P1 to PR are unit time Poisson process standard with rate 1, then we can actually express the state xt. So this will be the vector of all the copy numbers as the stoichiometric vector weighted by this process here. And the very nice thing is that this can be simulated exactly using Gillespie SSA, which I'm sure most of you are very familiar with. This is an exact algorithm for generating samples of this process. And of course, so this is a continuous time Markov process. Associated with it, there will be a Fokker-Planck equation, which characterizes the evolution of the probability density Pn of t. So Pn of t will give you the probability that the system is in state n, where n is the vector of copy numbers at time t. And it's characterized by the so-called chemical master equation here. So these are the propensities, and this is the stoichiometric, corresponding stoichiometric vector. Now, okay, so here I have kind of hidden out the fact that you have boundary conditions, but let's assume that those are implicit. And so this defines an infinite set of ordinary differential equations. If you were to solve this in practice, you would have to truncate the space at some point to get a finite set of ODEs, and so this is well known that there is a problem that in the sense that as the number of chemical species increases, you have a curse of dimensionality. The state space will grow exponentially with n. Of course, there are recent methods which can mitigate this. There's all these really nice tensor methods now. But yeah, traditionally this is a problem. Okay, so in many cases we would want to coarse grain the Gillespie SSA, and the reason is that if you have reactions which are very rapid, then you'll spend a lot of time having to handle those reactions, and computationally it becomes prohibitive. So there are many different options you can choose. One of them is the so-called chemical Langevin equation. So this is a diffusion approximation of the Gillespie SSA, and is valid if all in the regime where all species are abundant and under appropriate scaling for the reaction rates. And so yeah, this I think the first definition was in Gillespie's 2000 paper, but I know it's been then rigorously justified later in quite some detail. And it's given by this e to SDE here, where these lambda j tildes, they are just the propensities, but you have a smooth extension of them from the kind of the natural numbers to Rn. Of course, many people just implicitly do this, but that's not given. You have to choose an extension, and the way you choose it can have subtle differences on the dynamics. And the WJs here are standard Brownian motions. Now, if you're only interested in the statistics of the process, which is what I'm interested in, then the dynamics will be actually characterized by the generator of this process. And as we know, there are many SDs which will have the same generator arising from the different factorizations of the noise. And in fact, so this is one of them, one particular formulation for the noise term, which comes from Gillespie's original paper, and it's the one that we will use in this talk. But you can, like I said, you can choose various others, and this really nice paper by Benson Costas that describes equivalent formulations of the noise term. Okay, so that's also a continuous time Markov process, and it has associated with it a Fokker-Planck equation. And this is known as the chemical Fokker-Planck equation, which is given by this continuity equation here. So J here will be this flux, where D1 and D2 are effectively this will be the advection term, and this will be the diffusion term. Now here, as you will see, I don't really say anything about the boundary, and that's because there's no real when you do the approximation, there is no information given to you at the boundary. It's something you have to handle yourself, and there's really no way to make a decision. Anyway, so we'll talk about that later very soon. But so this is also a PD on Rn, where n is the number of species. If you were to simulate this, then you would also have a problem of recursive dimensionality. However, so for me, I'm more familiar with these methods, and I know that there do exist some adaptive mesh refinement methods and tensor decomposition methods which can mitigate this somewhat as well. Okay, so for now we're just going to focus on the stochastic, the SSA, and NCLE, and then we'll talk about the rest later. So what is the problem with the chemical Langevin equation? So the chemical Langevin equation is a diffusion approximation and is valid under those assumptions. But it will break down if those assumptions won't hold, and it'll break down quite significantly. So the first problem is what happens at the boundary. So namely, even simple reactions like this one here, it's not guaranteed that will satisfy positivity. And what that means is that it's quite possible that if you look at a chemical Langevin equation corresponding to this reaction, which is just given here, then you can, there's a non-zero probability, so that should be A there, that the state can become negative. So you have this non-physical configuration where your state, you have a negative copy number, which is something you really want to avoid if possible. So a clear possible solution is to reflect AT at the boundary. Or equivalently, if you're working with the Fokker-Planck equation, you would impose some sort of no-flux boundary conditions. And this is certainly very natural, because it means that your probability mass is preserved within this positive orthant. But even then, just because you're preserving, you don't have negative copy numbers, it doesn't mean that you will still get a good approximation. In fact, you can actually you can construct examples where the CLE provides an arbitrarily bad approximation. So one nice example is this one. Let's say you have, say, 10 independent subunits, each one consisting of a gene switch like this, and these will produce some protein P with rates either K1 or K2 depending on which state you're in. And the point here is that these transitions from G to G star are slow, right? So this is where the diffusion approximation will not be valid. So the kind of the discreteness of these switches here will be significant. And so if we set the total number of units to be 10, and we plot the stationary distribution for the protein, this is with reflective boundary conditions. This is what we would see for the chemical master equation. So you see this very multimodal distribution, which arises from the discreteness of these slow switching. The corresponding diffusion approximation, however, is just this unimodal distribution. And what that means is that, and you can make this worse, you can make this arbitrarily bad. So this is something I mean, it's obvious that diffusion approximation only applies in a very particular regime, but it's also worth emphasizing that you can make it as bad as you want. So if you modify K1 and K2, make this slower, it's just going to get worse. But even when you have large copy numbers, you can still do pretty bad. So it depends really what you're measuring. If you're measuring rare events, for example, the CLE is terrible. So for example, let's say you want to measure the mean extinction time, for example, for a birth-death process. So for example, you have a process like this. So you're producing K1 with A with rate K1, and it's degrading with rate K2. So it's described by this jump process here. Then you can actually write down explicit forms for the, and you want to measure the mean extinction time. So that's the average time it will take for the chemical species to actually hit 0. And so if you can actually write down explicit expressions in this case for the mean extinction time for the discrete process and the corresponding chemical Langevin equation. And if you solve these both explicitly, and so we assume that you start from the mode of the stationary distribution. So this birth-death process the stationary distribution will be unimodal around K2 on K1, and we assume that K1 is 1, so it'll have a mode at K2. So if you start your process from there and you measure the average amount of time it takes to hit 0, then for the SSA and for the CLE, you'll see drastically different results. And this is because effectively the chemical Langevin equation is not really able to capture the rare events that the SSA can capture. This is something that's well known, but it's worth reminding occasionally. Okay, so the thing is this: we still want to use the chemical Langevin equation because it's computationally quite efficient. So then the question is, how can we use both? So what we would like to do is we would use the chemical Langevin equation or the chemical Fokker-Planck equation in regions where the approximation is applicable. And in regions where it's not applicable, we would fall back to using SSA. And so you can imagine for a two-species system, you can imagine something that looks like this, a state space that looks like this. And then the question is, what happens at the boundary here, at the interface between the two? And that's actually quite non-trivial to figure out.
What are the dimensions, X and Y?
Oh, yeah, so this would be one chemical species, so this would be the copy number of one chemical species, this would be the copy number of another chemical species. So each point here is a state in the system. So this would be for the chemical Fokker-Planck equation. Okay, so what I'm going to talk about is a one hybrid scheme, which is for the SSA. And what we're going to do is the following. So for each reaction, we're not going to make any a priori decision on whether a reaction is fast or slow or a species is fast or slow. We allow everything to happen. So what we do is we introduce a blending function. So what is this? It's just a smooth function. You give it a point in state space, and it gives you a number from 0 to 1. And we will let this function decide whether a reaction is slow or fast. So when beta r is 1, so basically this is something that we choose, right? And the idea is that when beta r is 1, it is chosen when one of the involved species has low concentration. So when I mean one of the involved species, I mean either a species which is used in a reaction or is produced. So basically, if it's in the reaction, somehow it has to be, this beta r will depend on it. Beta r is chosen to be 0 when all of the involved species have high concentration, so that means that it is in a state which is valid for the chemical Langevin equation, and then you have this intermediate state, this intermediate blending region, where it is between 0 and 1 in a smooth way. And what we do is we decompose the reactions. So we have a propensity, we decompose the propensities. So we have propensity lambda f, we write it as beta r lambda r plus 1 minus beta r lambda r. And so we've done nothing here, we've just added and subtracted from the propensity. And so since we're only interested in the statistics of the process and not the actual parts, we're justified in writing this. So remember, this is the kind of the time change Poisson representation of the SSA. We're justified in writing it in this form. So basically, we express lambda j in terms of its this decomposition in terms of beta, and then we split it into 2. And of course, this is only valid because we're interested in the statistics and not the actual part. So then what we do is we yeah.
Make a quick point. Back up the previous slide. You need the PJs in your two sums to be independent.
Oh yeah, that's also true. That should be QJ. Sorry.
Yeah.
Very valid point, because otherwise you wouldn't be able to do this. So what we do then is we leave the first term as it is. I'll explain this in a second. And the second term, we apply diffusion approximation to that. So this is effectively the chemical Langevin equation applied to this term here. And we leave the first term as it is. And so what we get is effectively a jump diffusion process, right? So we have diffusion here, we have some advection, then we have these discrete jumps. Now here I have this little bracket here. So what this represents, it's the closest integer value to a given point in Rn. And we put that there because we want the jumps to really depend on the integer value that the thing is at. Because remember, lambda j is really only defined at those points. It's not defined. You can extend it, but we don't want to do that. We don't want to extend this to Rn. So this is the process. This is basically the first hybrid model we'll talk about. Okay, so let's just go back to the choice of blending region. We can now actually make it more explicit. So if you have, so like I say, if you have a reaction of this form, you want to choose beta r to be 1 if any of them are small, and small is kind of a problem-dependent label. You choose beta r to be 0 if all of them are large, and then you interpolate linearly in between. Now the problem is, depending what small is and what large is really a modeling decision. But the point is that it should depend on the reaction rate. So what you really want is that your inner, so here, if this is the state space, so for a two-species system, you really want to be in the region that's doing chemical Langevin if the value of the propensity is typically large in that area. So that would mean that you would choose this region according to the reaction rate. Because if you have a reaction where the reaction rate is very small, even though you have abundant quantities of each reactant or each reactant, you could still have a very slow reaction. So it's worth mentioning that. Okay, so what would a typical trajectory look like? Let's take this two-species reaction system of reactions. We have this dimerization reaction here, and let's say we start the process from the point 1, 1. What you'll see is a trajectory which is typically doing jumps, and then it'll enter the blending region. So there's a blending region for every single reaction here. The one I've illustrated here is the one corresponding to the second reaction, and so it will be 0. It'll take values 1 in this region, it'll take values 0 in this region, and there's an interpolation in between. And what you'll see is that in between you'll start seeing jumps and diffusion both at once, until it eventually wanders into the region where it just does diffusion. And it will go back in again, it'll do some jumps, and it might come back out. This is the idea of the hybrid scheme. Okay, so can we actually justify this approximation? In some sense we can, but I have to say it's not a very satisfying result. So what we can show is that if we assume that we have we're in a regime where the Fokker-Planck equation holds, so we're in this classical large volume limit where we can then, if we rescale the system, so if we write, so if our process xt is the SSA process, and we rewrite it in terms of concentration, and similarly we do the same for our jump diffusion process, we write it in terms of concentration, then what we can show is that you can bound the two in the weak sense with an error of order epsilon squared, where epsilon is 1 over the volume of the system. And so that's what we're able to show. And the truth of the fact is that if we didn't have any jumps, and it was just pure Fokker-Planck equation, we would get the same result. So if it was just chemical Langevin equation, you'd still get epsilon squared. So really, we haven't showed any superiority of our jump process over the chemical Langevin equation, but it's certainly not doing any worse. So that's one thing to mention. Of course, numerically, we see vast superiority. It's just that we haven't really been able to prove anything rigorously. Okay, so far we've only discussed an actual model. It's a jump diffusion SDE. We have to somehow simulate this thing, and unfortunately we're not in a position that we can simulate it exactly. So this will come at a cost. Okay, so I'm going to present two algorithms which are a bit different, and they both have different advantages. So the first one's based on the next reaction method, which might be familiar to some of the people in the audience. So it's based on the fact that we once again have this very nice representation for the SSA in terms of a time change Poisson process. And so what we do is if we generate a realization of this unit time Poisson process, to determine the next reaction, what you want to do is you want to find the time here such that TR of t equals that next reaction time. So really, let's say that f of r was kind of the last time that this Poisson process fired. Then the next jump time will be fr minus log u, where u is a uniform random variable. So this is just an exponential distributed random variable. And then the reaction r, the rth reaction, will occur at time t plus tau, where this relationship holds, where TR is this integrated time. And if we are guaranteed that no other reactions take place in this time, then we know that this propensity here will not change in that time. So basically lambda rxs between t and t plus tau is constant. So then we can always write tr of t plus tau in this nice form. And therefore, you can actually solve to get the next reaction time for the rth reaction explicitly. Now that's really good, and that's the basis of the so-called next reaction method. So I won't go through it. Of course, you will have multiple reactions, and then to guarantee that no reactions take place within that time interval, you always choose the first firing time that occurs, and you guarantee that nothing else can happen in that time. So this is the standard next reaction method. Now we want to do this with diffusions in it as well. So there is a nice algorithm by Dave Anderson which is called the modified next reaction method. And so the idea is that basically it's the same thing, it's just a bit more explicit. And the idea is that you don't necessarily, we have the same setup, so f of I will be the time of the last reaction, the next jump time will then be this again, and we want to solve this equation again. But now, so the point is that this term is no longer constant between time t and t plus tau, because this term, it depends on z, where z is this jump diffusion process. In particular, between these two times, even though no other reactions occur, there will be diffusive dynamics taking place. So this guy's changing. So we can't really solve this explicitly anymore for tau, and that's a problem. But we can always approximate it. And so what we do is we get that integral and we discretize it using a standard Riemann sum. And then we just find that the first, so we introduce a time step delta t. We also have to introduce a discretization of the SD, right? So we don't really make any claims to what that can be. That's really your choice. There are some good choices though. And we choose tau to be n min delta t, where n min is the smallest value of n, such that this relationship holds. So, and of course, if you take delta t smaller and smaller, this will become this will converge to tau. And so throughout the whole space, we want a good choice of discretization for the diffusive dynamics. Since we're only interested in weak errors, so computing expectations and things like this, we really just want an integrator which has good weak properties. And one of them, which is explicit and very nice, is this weak trapezoidal rule, which is based on this paper here. And that's an explicit scheme. It's a two-step scheme which is specifically tailored for the case where you simulate the chemical Langevin equation. Although I think you can actually use it in more generality. And so this is what we use for the diffusive dynamics throughout the whole state space. And okay, so I'm not going to go through the actual algorithm, but so the crux of the algorithm is what I described before, but we can also make some clever optimizations. So for example, if we're in a region where all the processes are doing just chemical Langevin equation, we can choose a slightly larger time step and do a macro step in some sense. If we're similarly, if we're just doing jumps and there's no diffusion, we can just use straightforward next reaction method. And in between, we have to do this idea that I just discussed in the previous slide. Okay, so that's one algorithm, but it has a drawback. And let me just go back one slide to quickly show you. This is an approximation which is quite a poor approximation of the integral. So these terms are not smooth. You wouldn't expect to have a derivative of this in time. So what will happen is that this will contribute an error of order root delta t. And it doesn't matter how good your integrator is, this is going to hold back this is going to contribute the significant part of the error. And because of that, within the blending region, you have to take delta t very small. So this is, although this method works in a lot of generality, there's really no constraints on it, this is kind of the bottleneck in some sense. But that's not really a problem. You wouldn't choose maybe the blending region too large, and it will just be a relatively small region, and then you can have large time steps outside that. Okay, But let's talk about another method which avoids that issue. And so this doesn't hold, so now this avoids that issue, but then there are some constraints. So if we are in the nice situation where we're just doing, where this function here, so it's the blending function times the propensity, they're all bounded, then, so let's say there's some gamma r such that this holds, then we can use this method called thinning. So the idea is that you would have this other process, qr of t, with a constant rate qr. And you would simulate that, so that's just a homogeneous Poisson process. You would simulate that, it'll generate a set of reaction points, and then you decide whether or not, based on your current state, whether or not you that a reaction did occur at that point or did not. And so, yeah, so basically what you do is you simulate the next reaction time, you will simulate Langevin dynamics up to that next reaction time, and then you randomly decide, it's kind of like rejection sampling, you randomly decide whether or not that state did have a reaction. If this condition holds, where u prime is a uniform random number, then you fire the rth reaction. If not, you don't, and you move to the next reaction of the dominating process. And you keep on going. This is good because you don't have to worry about solving that integral equation efficiently. On the other hand, and typically it's more efficient, because you can take delta t a bit larger. But on the other hand, there is a caveat that if you choose these upper bounds poorly, so if you choose this gamma r very bad, then this is going to be a rapidly firing process, and it's going to slow the whole thing down. And in that case, you might just want to use SSA. So they both require a bit of tuning, but they both have advantages in some sense. Okay, and so I'm not going to go through the algorithm here, but it's the same thing. But basically, like I said before, we can do some optimizations in kind of the specific cases when all of them are doing, all of the reactions are purely diffusive, so they're all doing chemical Langevin, or all of them are just doing SSA. And but otherwise, it's basically as I described. Okay, so let's talk about, and I think I'll just talk about the numerical examples and stop. So when do these hybrid methods have an advantage? They have an advantage when you're exploring all the regimes in your state space. So a typical example might be if you have a system where your initial condition might be quite large, in the sense that you start far out from the origin, and your distribution will then settle concentrated around 0, say. So this is one example of such a reaction here. I didn't list the reaction rates, but you can see what happens. So here I've plotted the distribution of the SSA over time. So from time 0 to time 100. And what you see is that you get this settling, so you start from this bimodal distribution, and you see it collapse into a unimodal distribution around the origin, like this. And if you do the chemical Langevin equation, in the regime of large volume, so in large concentrations, you see the same thing. There's absolutely no difference, and you wouldn't expect there to be. But as the process settles around the low concentration numbers, you start to see differences. And they might not be visible from a distance, but what really the CLE gets wrong is the tails of this distribution. Absolutely wrong. Whereas the hybrid scheme, like the two others, they agree perfectly for large concentrations, but once we're in the low concentration regime, it also agrees quite well with the SSA. But then again, when we were in the large concentration regime, we benefited from the efficiency of the CLE, right? We didn't have to do lots of reaction events like we did for the SSA. And more specifically, if we just, if we plot for different values of volume, we plot the mean and the variance, or the first and second moments actually, of the equilibrium distribution generated from these three methods. What we see is that as the volume decreases, the CLE gets it a bit wrong. It's significantly overestimating it, whereas the SSA and hybrid schemes seem to agree quite well. And you see the same thing for both moments. Of course, I don't make any claims that the process is ergodic. I can't prove that. I can't even prove rate of convergence. I can't even do that for the chemical Langevin equation. If anyone knows any results about that, please tell me. Okay, so another example where you see similar behavior is when you have these cycles where the chemical concentrations can fluctuate very rapidly from, say, I don't know, from low concentrations to very high and down again. Now, a typical example would be like a cell cycle model or a Lotka-Volterra model like we have here. And so this is a typical realization for this choice of parameters. See these large fluctuations. So the green and the pink, I think, are the species A and B respectively. And so this plot kind of gives some justification as why you'd want to use a hybrid scheme. This is a typical plot, a typical realization of your process simulated using SSA, and the heat map here is the average amount of chemical reactions that would take place within a time step of 10 to the minus 2. So if you're here, for example, within a 10 to the minus 2 time step, your SSA would have to have done around 1,000 reactions. So clearly you want to avoid that. If you can use like an SD or a chemical Langevin equation there, you would win something. And so that's the idea, that's really the motivation for the hybrid scheme. And so on the other hand, the chemical Langevin equation gets the boundaries very wrong. So what we see here, for time 1 up to time 6, we plot the average value of A of t, so the first chemical species, averaged over 10 to the 4 realizations. So what we see is that as time goes on, and it's doing these cycles, these very rapid cycles, at one point, due to these rapid extinction events, because that can happen with this process, the chemical Langevin equation gets it really wrong. And this isn't like a numerical artifact. This has been the time step has been refined very carefully to ensure that this is an actual behavior of the model. And so you can actually explain it through the fact that at the boundary, it gets one of the reactions very wrong, and it causes the process to go extinct. And on the other hand, what you see here is that the SSA and the hybrid scheme seem to agree very well. And so, and you get the behavior that you would expect. So this is the average value, and we can also plot the average computation time. So here we do the same thing, where we plot basically how much time it takes to perform that computation. And so the dashed line is the SSA, and as you can see, it's getting larger quite rapidly. The green dashed line here is the CLE, the chemical Langevin equation. We see it's pretty cheap. And so our hybrid scheme lies somewhere in between. So of course it has to handle rapid reactions occasionally, but not always. And what we see is that okay, so it's an order of magnitude more expensive than the chemical Langevin equation, but at many points it's an order of magnitude still cheaper than the SSA.
What is T again?
T? It's the time, amount of time. So this is a finite time simulation. Yeah, exactly. So so 5 is actually the average time it takes for one cycle. Yeah, exactly. So the period is actually 5. So here it's just started to do another cycle. And okay, so I should be clear, these are very bad implementations of all three schemes. So I'm comparing 3 bad. I'm being honest, at least, in the sense that I haven't chosen some state-of-the-art implementation of either of those. But anyway. Okay, so I think I should wrap it up very soon, I guess, right? It's
a couple more minutes.
Okay. So how does it do for rare events? And this is something we have no theoretical intuition about, in the sense that I can't really prove anything about it. But let's go back to the birth-death process that we had before. So we increase with rate. We do yeah. So we create A with propensity lambda 1, given by this. We degrade with propensity k2n. And so once again, we can, like I said, for the SSA and CLE, we can write everything explicitly and solve it. We can't do that for the hybrid scheme, but what we can do is we can simulate it and compare the results. And what I've done here, I have 2 plots. So here I have, you see these, so the 2 dashed lines are the lines that we had before for the SSA and CLE. We have these lines in between, these hybrid schemes. And the numbers there indicate where I start and when I finish the blending region. So 1, 2 would mean that from 0 to 1, I'm doing just jump process, SSA. From 1 to 2, I'm doing jump diffusion. and from 2 onwards is just chemical Langevin. And what you see here is that, okay, so if I choose my blending region to be too close to the origin, so there aren't many points that are just doing diffusion, I get an improvement over the CLE, but it's not really, it's not that accurate. But nonetheless, if I start pushing the blending region to the right, then I quickly get converged to the right value. Of course, I have to be careful here. If I look at this problem over larger domains, so I start my process from farther and farther out, so I don't know, some value from 10 to 50, I would probably have to keep on increasing the starting point of the blending region. So I don't think this is a uniformly good result. I have to be honest about that. But what we do see, which is really interesting, is that the size of the blending region plays a significant role in the error. So here, yeah, so what we see here, in fact, is that, is that right? Yeah, exactly. So here we take a blending region of size 2, and what we see is that for the same starting points, we get a significantly better error estimates. So we don't really we have intuition of why that's true, but we don't really have any estimates of the error as a function of the blending region, which is something you would want. Okay, so I definitely don't have time to talk about this, but we talked about the actual jump process, but there's nothing stopping you from applying a similar method to coupling the chemical Fokker-Planck equation with the chemical master equation. And so basically what you would do, this is your state space now for a two-species process. You would have, in the green region, you would have chemical Langevin equation. In the pink region, you would have chemical master equation, and here you would have some jump diffusion PDE. And I'm not going to tell you how to solve it, because that would take some time, but basically you can write down a jump diffusion SDE, and to solve it numerically, we use an interior penalty discontinuous Galerkin scheme, which works really well, and we get nice results. So I'll just show you that. Okay, so let me conclude. We have defined a very simple procedure that provides a good approximation to the chemical master equation or the SSA. The hybrid scheme doesn't require a priori knowledge of fast and slow species, nor does it require periodic repartitioning. So that's a good point, I think. And it doesn't appear to have the pitfalls associated with the chemical Langevin equation. In particular, it's provably always positive, and that's a good thing. So future plans would be to extend this to spatial problems, which would be quite useful. Extend to include other regimes. For example, you have a reaction rate regime. That would be. And Kostas is interested in approximate Bayesian computation and using this hybrid model for parametric inference. So thank you very much.
Yeah, so you show the sensitivity on the size of this blending region. So, but do you have any rule of thumb?
Yeah. So you basically want the wider the blending region, it seems the better. That seems to be the consistent rule, and we do have some justification for it in the sense that there are two sources of error. One of them is for discretization, because if you have a very small blending region, you have a very rapid change from 0 to 1. And that will obviously have effects on the discretization error. But even if you eliminate that, the approximation error, it also plays a significant role. So we don't understand that one quite well yet.
Thank you.
Why do you choose the blending region based on molecule numbers?
This is a bad idea. This is a very bad idea.
Yeah, because it should give you an absolute error, right?
Yeah.
Instead of a relative one.
So after we submitted this, we realized that this is a silly idea. What we should have is that the blending region should be a function of the propensity. This would solve all the issues with that. Yeah?
So is the fixing of these problems that you get by the blending region, is that due to the blending, or is it due to the fact that you don't start doing the chemical Langevin equation until bigger? And so what's the comparison between having nothing but chemical master equation in the whole region that's what you're both calling blending right now in chemical mastery.
You just have like a discrete kind of jump between the two.
Yeah, like I didn't quite.
Yeah,
what do
okay,
you
that's
have those three regions, and you're saying, oh, the blending helps. Do you mean you tested that by replacing blending with chemical mastery equation, or by replacing it with chemical Langevin equation?
Yeah, that's a very good point. I should have made that explicit. If you don't have a blending region, you just have a direct kind of transition between the two, you'll get extremely non-physical effects.
Okay, and where is that transition? Is that at the transition between region 1 and 2, or 2 and 3?
It's the so no. If you didn't have a blending region, you have a transition between SSA and chemical Langevin, right?
At which end of the blending region did you test there?
Sorry, I don't quite get your question. So
So you have three regions,
Yeah.
1, 2, and 3.
No,
So
not-
what he's
not if you-
asking is you replace 2, you drop 2.
yeah.
So do you replace 2 with 3 or 1?
Oh, both. It doesn't make any difference.
Oh.
Okay, so this is better than both of those.
Yeah,
Okay,
definitely,
cool.
definitely.
Great.
And yeah, so it's actually really nice to see why that happens. When you have either of those cases, what will happen is that at the boundary there'll be reactions that there'll be states which have twice as many reactions occurring at that state, because there will be local reactions from the diffusion and non-local reactions from the jumps. And so what you want to do is you want to weight them in such a way that the total number of reactions is the correct amount, basically.
One last question.
So a common situation that's encountered in some types of biochemical networks is that some species are low and other species are high. None of your examples were like that, and I was wondering if how much would you expect it would help in cases where there might be several orders of magnitude separation in the numbers of chemical species, say in a signaling network?
I would probably so this would work fine, because you would have a family of reactions which would be slow and a family of reactions that are fast. However, I think all the other methods handle that perfectly well too. So I wouldn't really want to sell this method as a solution, because I think like even the method like Hazeltine and Rawlings, they all do that very well. So just use one of those methods, I guess.
Let's thank Andrew again.